Okay, there we go. Looks like we got some video. All right, everyone, thanks for joining. I am Mike Saunders, Hardwater Hacker on Twitter. Today I want to talk to you about Buffer Overflow 101. We'll let you know that you can get these slides at redsiege.com/EIP, and those slides will have all the demonstrations that I did today, as well as links to the resources that I'm going to talk about and some practice resources that you can find at the end of the deck that you can use. So, standard about me, I'm principal consultant with RedSiege. Been in IT a while, been in security a while, and when I'm not doing the security stuff, you can probably find me kayaking or playing the guitars back there, or maybe out doing some baking. So, why am I talking to you about Buffer Overflow 101? This isn't a new topic. This has been around and it hasn't changed since Smashing the Stack for Fun and Profit came out in 1995. Well, the real reason I'm doing this is when I was learning buffer overflows, which honestly wasn't that long ago, I felt like buffer overflow was, well, I think this gift pretty much sums it up. It felt like magic to me. I knew that a buffer overflow was you had this buffer in memory and you took some data and you pushed too much data into that buffer and bad stuff happened. But I didn't understand any more than that. And as I was learning it and starting to get comfortable, I was noticing that, on Twitter, people that I follow are asking about buffer overflows, just getting started with it. And naturally, because of imposter syndrome, I assume that I know nothing and they know everything. If they're asking about buffer overflows, then why are they doing that? Because they should all know that. And these were people that had been around a while. And in talking to friends, just realized that this is a basic concept that a lot of us don't learn right away. Some of us don't learn for a long time. And there's so many new people coming into the industry all the time that don't have the background that there's always going to be a relevant topic, or at least, for quite a while. So that's why I'm talking to you about Buffer Overflow 101 now. To talk about that, I do need to get some assumptions out there. I'm talking about buffer overflows in a 32-bit architecture, x86 architecture. These aren't any kinds of advanced buffer overflows. We're not doing ROP chains. We're not doing SCH type things. This is a standard stack-based buffer overflow where we overwrite a return address and gain execution control. There are no protections in place when we're doing this. There's no depth. There's no ASLR. I happen to be doing this on a Windows XP machine, but this would work in Windows 10 as long as you don't have some kind of AV or EDR in place. It's going to block the buffer overflow attempts. This will also work. These concepts translate to things like ARM architecture or 64-bit architecture. They aren't exactly the same, but a lot of the concepts are similar. So you can use this as a starting point. So what is a buffer overflow? We should define that. This is not a buffer overflow. This tweet was gold. I was really glad I was able to snag it when Subt tweeted it out. So a buffer overflow, at its most basic, is a program incorrectly allows writing more data into a buffer than it had previously allocated space for. And that causes adjacent memory to be overwritten and possibly bad things to happen. So if you have 500 bytes that you write into a buffer, or you allocate 500 bytes for a buffer, and then you write in 600 bytes, you've written in 500 bytes and you filled up your buffer, and that additional 100 bytes goes into the adjacent memory there. So that's what happens when a buffer overflow happens. How you get execution control and actually exploit a system, we will walk through that, and I will talk you through how that works. Oops, wrong screen here. So before we do that, I have to give you some background. I talked about the stack a couple of times, possibly. The stack is a data structure. It stores data in contiguous blocks, and it's temporary storage in RAM. It's typically used to store local data, things like parameter values, data about the particular function that you're in, for instance, main and these various subroutines, each one will have its own memory space. Something called a return address, which we will get into. And an important thing to know about the stack is that it is a last in, first out architecture or data type. So if you think of going to a buffet and they have that stack of plates, and if you push down on it, it goes down and it pops back up. If you put 5 plates onto that stack and you push them onto the stack of plates, and that's the terminology, we push things onto the stack. If you want to get that first plate that you took off, you have to take off the previous 4 plates. You have to pop them off the stack. So the last thing to go in the stack is the first thing to come off the stack. And that will become important here as we walk through this. So I'm going to give you a visualization of the stack. This isn't entirely accurate, but it's going to work for our purposes today. So this is an example of a stack. I talked about main, right? So if you think about your main routine, that would be the parent routine down here. And let's say we had a subroutine just called process. This is the process subroutine here. We've called process, and this is its memory space. Process has a 50-byte variable foo. It's got some other things that are pushed on the stack like frame pointers and base pointers, and they're all important, and we're not going to talk about any of them. The thing we are going to talk about is right here, this return address. And the return address tells the program how to get back to the parent routine, how to get back to main, or whatever function called it once it's done executing. Now, some of you may be looking at this and thinking that I have this backwards. It's upside down. And you probably learned buffer overflows, or you learned about memory structure in school. And you'll notice up here at the top is all zeros, and at the bottoms is all Fs. So if you learned it in school, you probably learned with all zeros on the bottom and Fs on the top. And there's nothing wrong with that model, and it's probably a better way to do it. The reason I use this is how I learned. The examples that I followed laid it out this way, and the debugger that I use lays it out this way. So I'm going to use this model. Just be aware that as you're learning and you're researching, if you come across a scholarly article and you're used to using a model like this, they may have it flipped and it will be somewhat bewildering, and you'll think that everything you knew was wrong until you realize what's going on. So a few more things to point out. Because memory addresses are at the bottom in this model, if we were to pop foo off the stack, the memory addresses are getting higher, right? Like each entry in the stack has a higher memory address. And if we were to push more data onto the stack, for instance, like this, the memory address gets lower. Now, we've pushed bar onto the stack. You'll see that this ESP, or top of stack, moved. And ESP is a register, stands for the stack pointer, and it keeps track of where is the uppermost memory address of the stack. So if we push bar onto the stack after foo, ESP gets updated to point to this location. But if we were to pop bar off the stack, then now all we have left is foo on the stack, and ESP has been updated to point to the top of foo here. So the ESP will keep track of where the stack is at, where the uppermost address, or rather the lowermost address in the stack, if you're using this model. So ESP, address moves higher as the stack shrinks, address moves lower as the stack grows. There are other registers. The accumulator, stack pointer is the only one we're going to talk about. These registers historically had a more defined purpose. Nowadays, their use can be fairly flexible, and those decisions are made at compile time a lot of the times. There is a special purpose register called EIP. That is the extended instruction pointer. You'll notice all of those general purpose registers started with E for extended. That's because we're in the 32-bit architecture. If we were in 16-bit, it would just be the instruction pointer. The instruction pointer stores the address of the next instruction to be executed. It does not store the instruction to be executed. It does not store data about the instruction or anything else. It stores the address of the next instruction to be executed. It's an important thing to remember. It stores an address. If you can control what goes into EIP, you could control what execution is going to happen next. You can control what command is going to be executed. And contrary to popular opinion, you will hear people say, I overwrote EIP. I will probably screw it up and say it at some point today. You do not overwrite EIP, you overwrite the return address, which gets loaded into EIP. EIP, for the most part, can only be modified directly through the kernel. So let's take a look at a buffer overflow. What does it look like in the stack? This is a simple command line program running on a Linux system, but it would be not different doing it in a Windows environment. We talked about that parent routine process, right? This is the parent routine here, main. And main calls foo with one argument. That's an argument that it gets on the command line. And if we look at foo, foo declares one variable here, C. We're going to use stir copy, so we're not going to check to see if things fit. We're just going to copy what we received on the command line into C. And then we are going to print what's in C out to the screen. Now you'll notice there is no return here. We're not nothing says return back to main. That's because that is built in at compile time, the instruction on how to get back to main. And where it will go to will be immediately after what called it. So it called it here, it'll go to the next instruction, return 0, and then we'll exit the program. And it knows how to get there because of that return address. And we'll take a look at that. So this is what the stack for the program would look like for the most part. We've got our parent routine stack down at the bottom, which is going to be main, and this is going to be foo. And here's our variable C. We've got some other things below C, and then we've got the return address. That's what tells it how to get back to main. Now, if we were to run this program, let's run demo hello. It runs, it prints out hello to the screen, and it exits normally. It's what we would expect to happen. We didn't put too much data in, shouldn't be any problem. And if we were to look at the stack for the program, we'd understand why. We put in hello, we put in 5 bytes. There's actually a 6 byte here, and that is because strings in C and C++ are null terminated. So we pushed in hello in our null terminator. We did not fill up the rest of this buffer. So that C was popped off the stack, and then the rest of the data was popped off the stack. And the return address popped off the stack, loaded into EIP. That takes us back to main, and we exit out of main. But what if we gave it too much data? In this case, 16 A's and 4 bytes of hex CCs. I run that. We print out the A's and the hex to the screen, and then there's a segmentation fault. And think about that order that I just said. I ran the program with the input. We printed the data out to the screen. We put more than 12 bytes into the buffer. We put 20 bytes into the buffer. It still printed that out to the screen, and then a segmentation fault occurred. And if we look at our code, we can understand what's happening here. We push this into the buffer, and then we printed it out, and then the segmentation fault happened. It's an important thing to know. It's an important but subtle distinction. And if we look at the stack, we understand why. We've got 12 bytes of A's. We've filled up our buffer, but then we pushed in another 4 bytes into what was a base pointer or a frame pointer, something like that. And then we pushed in these hex CCs that overwrote the return address. So at that point, when that return address was popped off the stack, EIP would have been CC, 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 CC. And that is not a spot where code for our program lives in memory. And therefore, the program doesn't know what instruction to execute next, and it crashes. That is a buffer overflow at its most basic. So let's see if we can weaponize that. I'm going to pray to the demo gods. I've got a backup presentation. So we're going to go over here, and hopefully this all comes through. I've got a Python script, and I will have a link to the Python scripts that I use during this talk available for you at the end of the talk. So I'm going to fuzz the input length of this program. Actually, you know what? Before we do this, let's go back. Let's talk about this. I'm going to do a demo with a program called vulnserver. Vulnserver is written by Stephen Bradshaw. It's an intentionally vulnerable program that allows you to learn how to write buffer overflows. If you think of how a web server works. If you were to netcat to the port and you have a verb that you give it, get, and then you have a couple of arguments. You have what you want to get, slash, and then the protocol you want to speak, HTTP 1.1, HTTP 1.0. You hit enter and that sends a carriage return line feed to the server. That tells the server, hey, I'm done sending you input, you can go ahead and process. And then it sends you whatever you requested. In much the same fashion, Vuln server has a suite of verbs. One of them is trun. And if you enter trun space period, the server processes whatever data is after that period, and it signifies the end of the input by sending a carriage return line feed. And then it will process that data, say trun complete. So what we're going to do is we're going to fuzz the input length for the trun command. So we're not fuzzing like a protocol here. We're not doing, you know, some wire protocol fuzzing or PDF or whatever. We're fuzzing the input length. So this Python script sets up a counter. And yes, Python 2 point whatever, I know, needs to be updated. We've got this counter that we set up, and it initially sets at 100. We've got our command, trun space period, and we set up an empty list called buffer. We're going to populate that list with entries that consist of our command, trun space period, and some number of A's, which is A times the counter. And then we're going to increase our counter, and the next line in our list is going to be trun space period with 200 more A's. And we're going to continue on until we fill that up. And then we're going to take and send this data to the server. We're going to connect to the socket. We're going to send our data. We're going to receive a response, and we're going to print it out to the screen. So we're going to look at a debugger here. We're going to look at the immunity debugger. You can see that Vuln server is running. I've got it loaded. This here that we're looking at, that's actually the assembly language code right there. That is push EBP and, you know, move EAX. Those are assembly language instructions that are translated from our code. And that's how this program works. I mentioned registers. That's what's over here. These are the registers. So we've got EAX and ESP, our stack pointer. That's one we're really going to want to pay attention to right here. Stack pointer pointing to 22 F3AC right now. We also see EIP. So this, because we know that EIP contains, memory addresses of the next instruction and not the instruction itself. This is a memory address that lives in NTDLL, and that's the next instruction that the program is going to execute. And we can go here, we can look at the stack, we can follow and stack. So this is our stack here. This is where ESP is currently pointing. We can see that there's data in the stack here. Our program's running, everything's fine. So let's go ahead and run this. We're gonna run the module. We're gonna see that it sends a bunch of input, right? So it starts at 100, then 300, 500, and it keeps saying trun complete, just like we expected, until we get to here. At 2100 bytes, we send input, but we don't get any response back from the server. Now, if we were to go and take a look at our debugger, we see that it is paused now. And we see access violation when executing 41, 41, 41, 41. That means access violation when trying to execute the command that lives at 41, 41, 41, 41. We go up here, there's no code. There is no code here. And if we look at our registers, we see some interesting things. We see that EAX has our command. And then we see that ESP is pointing to a location that's filled with A's. That's what we sent the server. One other thing I want to point out here is that EIP is also 41, 41, 41, 41. That's what this means here. That means EIP was populated with a memory address where it didn't know how to find code. Now, if we were to go and look at this, we'll follow it in stack. We see here's our stack. So this is currently the top of the stack. We can see that there's a bunch of A's that happened before there. And if we scrolled up far enough, we'd see trun space period. And then we can see that there are A's afterwards. Now, we know that from what we've already talked about, the return address is something that gets pushed on the stack and then loaded into EIP. So it's just a memory address that's pushed onto the stack. If EIP is 41, 41, 41, and we see that all these are 41, 41, 41, and these are all A's here, that means that we have overwritten the return address with our capital A's, and those capital A's were loaded into EIP. This is an ASCII capital A in hex. That's what 41 is. So we have overwritten the return address, which subsequently got loaded into EIP. We don't know how much data it took to get there. We don't know anything at this point. We just know that it was possible to do this. So the key points here, it took between 1900 and 2100 bytes of input. And when that happened, EIP is overwritten with our A's. So how do we find out if it's possible to know exactly how much data it would take before we overwrote the return address? There are multiple ways to do it, and I cover a different way in the slides that you can download, but here I'm going to use pattern create, which is a Metasploit utility. It will create a non-repeating string of characters up to about 20,000 bytes before it starts to repeat. I forget exactly where it's at. But you can see here, I ran the command pattern create -L 2500. It created this capital A, little a, 0, capital A, little a, 1, so on and so forth. And we're going to send that to the server and see what happens. So I've got another Python script here, and I look at my Python script. I don't have a list anymore because I'm just going to send my command trun space period. I'm going to add that string of characters that I generated with pattern create, and I'm going to send that to the server. You see that Vuln server is running. So let's go ahead and send that. We send it. The program has crashed. And if we go over here to our debugger, we see that it is paused. Access violation when executing 396F4338. Look up here, there's no code. We see that EIP is what we expect, 396F4338. Excuse me, EIP. And if we look at ESP, we see it's pointing to this memory location that's filled with capital C, lowercase p, 0, and a C. So let's go ahead and look at this. Let's go down right here. We see a bunch of data in the stack. And if we look immediately before where ESP is pointing, so if you remember that slide about the top of stack, this is where the top of stack is pointing right here. We see here 396F4338. It's the same value that's in EIP. In fact, that's because this is where the return address lives in the input. We loaded that return address into EIP, and then it crashed, 396F4338. Now, since we know that those 41s were actually the capital A's, this must be ASCII hex representations of ASCII characters here. And in fact, they are. A 39 is a 9, a 38 is an 8. But wait, if we look here, it's 8C09 or 8C09, but we look here, the 9 is on the left and the 8 is on the right. The reason is because we are on a little endian system. So data gets pushed onto the stack in reverse byte order. If we were big endian smalls and poppin' mainframes, our stack would be, or our system would be big endian, so we would just push it in the order that we wanted. But it is not, it's little endian, so we have to push it in reverse byte order. Helpfully, Immunity has reversed that for us. So we know now that this is where that's occurring. We still don't know how many bytes it is, but we know that as soon as the overflow occurs, the stack pointer is pointing to the next section of data after where the return address was. We're going to write down 396F4338. We're going to go back and look at another utility. Now, what we're going to look at is the complement to pattern create, which is something called pattern offset. We run pattern offset -Q 396F4338. It tells us the exact match is at offset 2006. So what that means is it took exactly 2006 bytes of input before we reached the first byte of our return address. So knowing that, if we were to say put in 2006 A's and then 4 B's and 50 C's, the return address should be populated with 42, 42, 42, 42, which means that's what EIP should be when the program crashes. So let's take a look at that. Got another Python script here, and that's exactly what we're doing. We're sending our command, some 2006 A's, 4 B's, and a bunch of C's. And we expect the EIP will be 42, 42, 42. All right, so let's look. Access violation when executing 42, 42, 42, 42. So now we know that it is exactly 2006 bytes before we reach the first byte of the return address. EIP is 42. We see that the stack pointer seems to be pointing to a location that's filled with C's. We follow the stack. We see, just as we expected, the B's were right before the C's started. So now we know that when the program crashes, data that we control was loaded into EIP. And immediately following that is where our shellcode could go if we were able to inject shellcode. And the stack pointer is pointing to that. So it would be really cool if we could have a way of telling the computer, go to where ESP is, go to ESP and execute code. And in fact, there is an instruction called jump ESP that tells the processor, jump to the location that ESP is referencing. So we can go to ESP, but we can't just put jump ESP in. I'll show you how to look up the opcode for that, because that's going to be important. But we can't just put that into these bytes where the B's are. Because remember, that return address is exactly that. It's an address. It's not an instruction. So we can't put the opcode for jump ESP in there, because we're just going to get an access violation when trying to load whatever that opcode is. So we need to find the something called NASM shell. Excuse me. Another Metasploit utility, if we use NASM shell and we put in jump ESP, it will tell us that the opcode for that is FFE4. So we can't put FFE4 into the return address, because the computer's not going to know what to do with that. We need to find a memory address where the FFE4 lives. So to do that, in Immunity, I'm going to use a script called Mona. Mona is written by Corlan, some great people. Peter is wonderful. And if we load Mona, one of the things we're going to do, got a clue right here, modules, C, Windows, System32, users, 32.dll. Going to run bang Mona modules. And modules are DLLs and other bits of code that are loaded with our program. That these DLLs are needed for our program to run. Like if we want to have networking, we're going to need networking capabilities loaded by DLLs. So we see a bunch of, things that probably look familiar to a lot of you: user32 and NT-DLL, kernel32 DLL. Most of these all look familiar, and then we see Vuln server itself and something else called ESSfunc.dll, which happens to be, it looks like, part of Vuln server. Now over here, these are memory addresses. These are memory addresses where that DLL is living. So if we could find a location within this memory, space of memory, that has a jump ESP, we could use it. A couple of things to point out. One thing we want to pay attention to, ASLR. There's no address space layout randomization, meaning we don't have to deal with that, because this is 101 level. Another thing to point out here, OS DLLs. So OS DLLs means that these are loaded with part of the operating system or not, like our program here, a third party that we've loaded. Now, what we want to look for is a jump ESP and FFE4 living in one of these modules. These OS DLLs could be used for finding a jump ESP. And we could do that. Let's say we find a jump ESP in user32.dll. I could use that right now, and that would be fine. The problem is that these addresses vary depending on what patch level on, what service pack you're on, even what language pack you're on. If you're running XP Service Pack 3 French language pack and I'm running English, jump ESP might be in a different location for you than it is for me. And that's part of the reason why, if you've ever used Metasploit and asks you to select your target, sometimes you need to do that so that it knows which return address to use for that particular exploit. So we could use these, but we don't want to, because we would have to be able to fingerprint the target to know exactly what OS it's running and patch level when we want it exploited. But if there happens to be one here in essfunc.dll, we could use that one, because this is something that's bundled with our program. It's going to be there as long as we're running version 1.0 of Vuln Server every time. That jump ESP should be in the same place every time. So we can use Mona to find those. So we're going to use another command, Mona find -s. Whoops. Remember that our opcode is FFE4. And then we use -m essfunc.dll, tells it to search within that module. So we run it, we find a total of 9 pointers. So that means there are 9 jump ESPs in this particular DLL. You can see here the first one's 6250 11AF all the way down to 6250 1205. They're all happening to be living in a place called page execute read, meaning we have executable memory. So we can load this address, for instance, 6250 11AF. If we put 6250 11AF into the return address, 6250 11AF will be loaded into EIP. The processor will then say, my next instruction is at 6250 11AF. It'll go to that location. It will see that that location says jump ESP. It will now jump to where the stack pointer is pointing to, which happens to be the start of our shellcode. So this is all we need to be able to exploit the system. We just need to build the shellcode in the right manner and put everything together. So we have one more piece to do that. I've got a proof of concept that will pop calc or something like it. So I've got my command, trun space period. I generated some shellcode with MSF Venom. And I used platform Windows, architecture x86. I'm using the Windows exec payload, and I want to run command.exe/c calc.exe. I'm going to pop calc. Exit func equals thread I will talk about. And I know there are some of you in the chat right now that are much better versed in this than I am, so feel free to clarify if I'm screwing up some of this language at some point. So we're using exit func equals thread, and I'll tell you why in a little bit. -e encoder, I'm going to use the x86 Shikata-Ganai encoder. -b means bad characters. Now you remember I told you that strings in C and C++ are null terminated. That's what this is right here. It's a null terminator. Reason we don't want our shellcode to contain a null terminator is because that would signify to the server, be like, oh, hey, there's the end of the input. I can start doing my thing, and it would drop. It would just truncate off the rest of our shellcode, and nothing's going to work. We also have 0A and 0D, carriage return and line feed, because we know that our protocol signifies the end of input by sending a carriage return line feed. So we don't want our shellcode to contain any of these characters so that we don't get truncated. Now, I'm going to run this. This is my shellcode here. This is my return address right here. And remember, it's a little endian system. So 6250 11AF is backwards. We need to push it in reverse byte order. So now what we're going to send to the server is our command trun space period. We're going to send in 2006 A's. You don't have to use A's. You could use any number of characters, right? I'm just using A's to make it easy. My return address is going immediately after those 2006 A's. I'm going to use 8 hex 90s, no ops or nops. They just tell the processor, don't do anything. And the reason why I will explain in a minute. And then after that is my shellcode. And then I'm just going to send that to the server. We know that we're running. So let's go ahead and send it to the server. Sadly, this doesn't come to the foreground like I like it, but I got to click on it. But that is the exploit. We just exploited Vuln Server, and we displayed this instead of popping calc. And the reason I chose this is because honestly, that's still kind of how I feel every time I get a buffer overflow working. And this is how I felt most definitely the first time I ever did. I did the shell dance in my office when I got that, because it was a magical feeling when I went on my own without following someone's instructions. I took the things that I've talked to you about here and I learned how they work. And I practiced and I found a buffer overflow in a program that wasn't Vuln server. And then I figured out how much data did it take till I could overwrite the return address. And then I located a jump ESP. And then I put it all together with shellcode, and then I was able to. It was absolutely magical feeling. And so that's why I decided to choose this instead of popping calc. Now, one fun thing I want to point out, if I can find my mouse, there we go. We look down here, we're still running. Vuln server didn't crash this time. And if we look here, we have an idea why. Thread 9E4 terminated. Now, if you remember back in the code, I used, boy, where did that go? Wrong one. I use exit func equals thread. That tells Metasploit to generate code to generate a new thread. So my exploit takes place in a new thread, and execution control returns back to the program, and the program doesn't crash. If I had done process, then the program would crash when I closed Explorer. So I chose thread because I want the thing to keep running. Now, the other thing that I want to show you is because I did that, I can run it again. I can go back, I can run it a few more times. And we're still running, and every time we're just generating new threads, and then they're executing, and the program's still working. The other thing I told you I'd tell you about is why I had those hex 90s in there. Now, the hex 90s are in there because they're just telling the processor not to do anything, but they're really there because they're scratch space. We used an encoder, and when you use encoded shellcode, it's just like base 64 data, right? It's encoded, but you can't do anything with it until it's decoded. Our shellcode has been encoded, so it's not actually shellcode, it's something that's encoded. What there is a little bit of a stub at the beginning of the shellcode that tells the processor how to decode the rest of the shellcode. And those NOPs are in there for a scratch space so that we don't overwrite our shellcode. Just gives us the space to decode without decoding over ourselves and clobbering our exploit. So when we put this all together, we've gone from, hey, what is Vuln server, to, hey, I know how to fuzz this application and I can make it crash and I can exploit it and make it still run. So what do you do after this? Like, okay, I learned Vuln server, but what do I do next? There are places that you can go to find vulnerable programs. There's lots of them on the internet. One fun place is just going to exploit database. You can search for these old buffer overflows, look for the early to mid 2000s buffer overflows. Some are even later than that. But you've got these buffer overflows, for instance, in Minishare. The nice thing about this is you can download the vulnerable application from exploit database. And you can use their buffer overflow that they've got in exploit database as a starting point to just help you understand and then start working on your own. Excuse me, but you can download these programs and you can fuzz them using the exact same process, excuse me, I showed you. There's even a bunch of MP3 players back in the mid 2000s that were vulnerable to buffer overflows because of these badly formatted M3U playlists. The process for doing that is not fundamentally different than what I did here. It's just that instead of sending a bunch of data to a socket, we would have to generate a bunch of M3U playlists and then open up each one of them until we figured out how much data we needed to overwrite the return address. But you can take this process absolutely and use this to do your own buffer overflow on a vulnerable application. So I told you there would be some resources, and those are coming up, but I do have to thank some people. Stephen Bradshaw for writing Vuln server, something that I could use to start practicing buffer overflows. If you know Peter, Corland Coder, a wonderful human being, and full of excellent information about buffer overflows. Learned a lot there. Ron Bose, Skull Security. If you know Ron, Ron is another wizard and has a lot of great information on the Skull Security Wiki. I also want to thank these people for, these are some good friends of mine that they encouraged me to do this talk and then spent a lot of time helping me refine this to make sure that what I was telling you was exactly the information that you needed without being too much, without leaving things out. So thanks to all of these guys. You can download Vuln Server at that link, and you can download Mona from Corland's GitHub. And then there are some buffer overflow blogs that you can follow. The first happens to be Stephen Bradshaw's, and we'll walk you through various kinds of buffer overflows with Vuln Server. Corland also has a great series of buffer overflow tutorials that go from easy to progressively more complex. And there's another one from Security SIF there as well. And by all means, just search on the internet, you'll find so many. Know that some of them are poorly written, and that's just how it goes. And some of them are really well done. Here's some resources, just background material for you, stack buffer overflows and how the stack works, and then a link to some fundamentals from Skull Security. And there are some other places you can practice. Over the Wire still has the Over the Wire Wargaming Network that has things like Smash the Stack war game and other games on there that you can practice buffer overflows and other kinds of security relevant skills. There are also VMs you can download on VulnHub that have buffer overflows in them that you can attack. There also are, I believe they're still there, and I think they're available for the free accounts, buffer overflow resources at Hack the Box. I know that they've had them in the past. I haven't checked quite recently, but I believe they have them there. So with that, I apparently was really juiced up because I'm about 3 minutes ahead of time. But someone just asked, will the slides be available? Yes, if you look at the slide that is on the screen right now, you can get the slides at redsiege.com/EIP, and you can get the, you know what, that link for the source is wrong. I'll have to update that and I'll tweet it out. You can follow the Hardwater Hacker Twitter account or the Red Siege Twitter account, but it's actually I want my EIP with underscores instead of spaces, or just go to github.com/hardwaterhacker and you will find the Python scripts that I used here, and do not judge me based on the code that you find in that repository because I'm a hacker, I'm not a developer. So if you have any questions about this, feel free to contact me. Reach out to me on Twitter. Please, if you want, follow the Red Siege Twitter account because that will give you information about our new blogs that are coming out and when we're doing our free webcasts. And I'm all about helping people learn because that's how I got here. People helped me learn and answered questions that, quite frankly, I just didn't know where to go. People helped me, and I want to try to return that. So feel free to contact me on Twitter or whatever. My contacts information is here on the slide. So that's all I have at this point. And yeah, Chris, I'm going to have to rewatch it again. That's how it is for me. It took quite a while rewatching it at speeds. So I want to thank all of you for being here. Thanks CircleCityCon staff and volunteers for making this possible. I really wish that my first CircleCityCon had been in person, but you know what? This was pretty awesome. So that's all I have. Help me out, CircleCityCon staff, if we're doing questions on the air or if we're moving over to the track. Just let me know.